At 1:23 and 40 seconds on 26th of April 1986, a button was pressed inside Chernobyl Reactor 4. It was the emergency shutdown. Every control rod was ordered into the core. The nuclear reaction should have stopped. 3 seconds later, instruments detected a reactor runaway. Seconds after that, fuel channels began to rupture. Then the reactor exploded. Chernobyl did not begin with that explosion. It began years earlier, when engineers discovered that the emergency shutdown could briefly increase power. The warning was recorded. The reactor was left unchanged. This is not simply the story of a reckless test. It is the story of a safety system hiding a fatal first movement. Reactor 4 was due to shut down for maintenance. Before it did, the plant planned one final test. A reactor still needs electricity after it stops generating power. Pumps must keep coolant moving until emergency generators take over. The test asked whether a slowing turbine could bridge that gap. Its remaining momentum might keep the pumps running. The idea was reasonable. Previous attempts had failed. Now the plant would try again. But the program was treated too narrowly. It was described as an electrical test. In reality, it changed the power supply to major reactor systems. It also affected protection and interlock systems. The test was touching nuclear safety. The planning did not fully treat it that way. Power reduction began on the 25th of April. By 2 p.m, the reactor was approaching the test conditions. Then, the regional grid controller ordered a delay. Electricity demand was still high. The reactor remained at reduced power for roughly 9 hours. At 11:10 p.m, the shutdown continued. At 12:05 a.m, power stood at 720 megawatts thermal. The intended test level was around 700. Then, at 12:28, control was transferred between automatic systems. Power collapsed from about 500 megawatts to roughly 30. For several minutes, the nuclear reaction had almost collapsed. That should have ended the test. Instead, the operators began raising power again. But the reactor had changed. At low power, Xenon 135 accumulated inside the fuel. Xenon absorbs neutrons. It suppresses the nuclear reaction. To overcome it, more control rods were withdrawn. Power stabilized near 200 megawatts. The reactor was running. But it was no longer in a normal condition. The key measurement was the operating reactivity margin. It represented how much control authority remained inside the core. The minimum allowed margin was equivalent to 15 control rods. Later calculations placed the margin near 6 to 8. The operators did not have a clear live number. The plant computer took roughly 10 to 15 minutes to calculate it. There was no alarm that forced an immediate shutdown. The reactor could enter a state its emergency system could not safely control. Some protections had also been altered for the test. Those decisions mattered. But later investigations found that several alleged violations were not the direct cause of the explosion. The deeper problem was worse. The operators had entered a trap they had not been fully told existed. The RBMK used graphite to slow neutrons. Water flowed through the core as coolant. That water also absorbed some neutrons. When the water boiled, steam bubbles formed. Steam absorbed fewer neutrons, the graphite kept slowing them. Under certain conditions, more steam created more reactivity. More reactivity created more heat. More heat created more steam. This was the positive void coefficient. At the time of the accident, both the void and power coefficients were positive. The reactor was not resisting a rise in power. It was helping it. A brake pedal had become connected to the throttle. At 200 megawatts, with too many rods withdrawn, the core was unstable and uneven. Power could concentrate locally. Low-power instrumentation could not clearly show every change developing inside the core. The reactor was now difficult to control. But the greater danger was hidden inside the system meant to stop it. The emergency rods were designed to absorb neutrons, but each rod had a graphite displacer beneath its absorbing section. When the rod was fully withdrawn, water filled part of the channel below it. As the rod moved down, graphite entered first. It displaced neutron-absorbing water. For the first moments of shutdown, reactivity could rise in the lower core. Only later would the absorbing section arrive. Full insertion took about 18 seconds. In the condition created that night, those first seconds could be catastrophic. This defect was known before Chernobyl. A positive shutdown effect had been identified at the Ignalina RBMK plant in 1983. Other RBMK plants were informed. Design changes were promised. Restrictions were proposed. The rods were not redesigned. The restrictions were not properly added to plant instructions. The assumption was that the dangerous conditions would never appear together. On the 26th of April 1986, they did. That was the first critical mistake. A known defect remained inside the reactor's last line of defence. At 1:23 and 4 seconds, the turbine valves closed. The rundown test began. 4 coolant pumps were powered by the slowing turbine. As it lost speed, their output began to fall. Steam conditions inside the reactor started changing. For 36 seconds, the test continued. Then the emergency shutdown was activated. Investigators could not establish with certainty why. It may have been the routine end of the test. It may have been a response to instability. What matters is what happened next. The rods began descending. Their graphite sections entered the lower core. Water was displaced. Reactivity rose locally. Power shifted towards the bottom of the reactor. Within 3 seconds, runaway and overpower alarms appeared. Recorded thermal power exceeded 530 megawatts. Then the instruments lost the race. Local power rose many times over. Fuel ruptured. Water flashed into steam. Pressure tore through the channels. The reactor came apart. The shutdown did not create the whole disaster. It connected every earlier weakness at once. The first Soviet explanation concentrated blame on the operating crew. The reactor had been taken outside its rules. Protections had been altered. Too many rods had been withdrawn. That became the accepted story. Later investigations changed the balance. The rules were incomplete and sometimes contradictory. Important reactor behaviour was missing from operating documents. The reactivity margin had no automatic trip. The control rods could initially add reactivity. The positive shutdown effect had already been observed, and the designers had not corrected it. The later international review described a combination of design defects, operator actions, and a wider failure of safety culture. The operators helped create the dangerous state. The system made that state possible. Then its final protection made it worse. After the accident, RBMK reactors were modified. The void effect was reduced. Control rods were redesigned. Shutdown speed was increased. A faster protection system was added. Reactivity margin information was improved. Every major change answered a weakness that existed before the explosion. The test was delayed. Power collapsed. The reactor was forced back to 200 megawatts. Xenon poisoning demanded more withdrawn rods. The reactivity margin fell below its safe limit. The positive void coefficient turns steam into feedback. The control rods carried a known shutdown defect. The warning had not become a redesign. Then the emergency shutdown was pressed. The explosion came last. The failure began when a known flaw was left inside the system designed to save the reactor. That is the failure chain. Ariane 5 also carried an old design decision into a new system. That failure chain is on screen now.